Hello there, thank you for joining me again today. Welcome to the wonderful world of electronics engineering. On the bench for repair is a RAPID power supply. These power supplies come in various names, brand names, badges for different manufacturers, model numbers, etc. But basically a lot of these supplies that look the same with the ammeter and all the presentation on the front are the same innards. There's a generic Chinese manufacturer, I believe, that years ago manufactured many thousands of them for different companies, so they are common on the market, mainly used for powering radio communication transceivers around the world that need high current output, providing from a power supply due to many radio transmitters using high RF output powers requires quite a large current power supply in order to meet those demands. This one has a variable voltage control on it, where it can go up to around about 20 volts and as low as probably 10 volts, with a little notch in the top there for 13.8, which is what most radio communication transceivers operate on. This one's got a little fault label attached to the top which says that the voltage is high coming out the terminals. So we're going to look at that in a moment, then do some repair work. These power supplies provide, as I say, up to about 30 amps continuous output power. They're a very well-known power supply in the world of radio communications. They're used by commercial customers, ham radio operators, marine radio operators that have home-based sets. They're used in electronics hobbyists, on bench power supplies, all kinds of different applications. Quite a very compact little power supply for its size, as you'll appreciate. Having such a small compact power supply with fan cooling that can provide 30 amps is actually quite an achievement, especially at this size. So if we zoom in on the label on the back there, we can see that it's the company RAPID in this particular case, DC regulated power supply. The output is 3 to 15 volts adjustable, 25 amps continuous, and that's basically the information there on the label. We've got a nice fan, a fuse for the mains input, so quite a nice compact power supply. It's quite a heavy power supply, weighs about 15 kilograms, something around about that, 15 to 20 kilograms. So although it's small in size, it does weigh a large amount. Now, it's a linear power supply, it's not a switch mode power supply, and that's a real advantage when you're working with radio communications equipment, especially at HF frequencies, where the power supply might be used in close proximity to the radiating antenna, be it a long wire, log periodic, antenna arrays, vertical antenna arrays, and of course RF from high powered HF and VHF radio transmissions can make it onto the electronics inside switch mode power supplies and upset them. And not only that, the noise from a switch mode power supply as well can induce interfering radio signals on HF frequencies due to the switching frequencies and harmonic content of the switch mode pulse width modulator. So by having a linear power supply, does away with both transmit signals getting into the unit and causing problems with regulation accuracy, as well as with reception, not producing radio frequency interference, disturbing receivers. So that's one of the reasons why these power supplies were made. Right, so the next thing we'll do is hook it up to the voltmeter and test it with that and see what output we're getting, and see whether we can confirm this fault that's written on this label here, which says high output on there. So have a look at that next. Back soon. Okay, so we've got the output of the main connectors there, connected straight up to the voltmeter. So what we'll do, we'll just switch it on. We've got it all plugged in. Straight away the meter's going right up to the end, and we're getting 23 volts out roughly. We can't adjust the supply voltage, so unfortunately it looks like as if there's no regulation. I'll just turn it off because I'm conscious that there could be capacitors on the output which are not rated to that level of voltage and could blow, so I'll just switch it off just for the time being. But as we can see, we can't vary the regulation, and the output is constantly high no matter what position the potentiometer is. So obviously that confirms the output voltage is fixed. We can't alter it, so I'll switch it on again 23.45 volts, just it to maximum. It's not going up or down, the voltage isn't changing. So yeah, also we've got the overload light coming on, or warning light there, which is what that LED is for. So if we just zoom in on that, you can see, yes, so we've got that warning light on there. So that's worthy of investigation, obviously, as part of this fault. So it's obviously an over voltage sense. So back shortly when we've got the lid off and have a look inside. Okay, so I've got it unplugged now. Obviously we're not going to have it powered up while we're looking inside and working on it, obviously. Word of caution really regarding safety on these. Obviously we've got exposed live mains inside various places which we'll go into. Very, very dangerous because obviously the case is earthed, so if you were to get yourself across the mains and then earth, then the potential for severe electric shock is on the cards. So where possible, power these up using mains isolating transformer with a 1:1 ratio, so that in my country here in England, for example, it was 240 volts AC, so it's naturally going to give you a nasty shock, whereas I know other countries might use 120 volts, 110 volts AC, etc. Sort of half the voltage that we use in the UK, but 240 volts AC is quite lethal. So that's why we always use an isolation transformer on the bench, and we exercise caution when working inside units like this. We've got the mains input here on the back where the cord comes in. The cables come down here and to the mains rocker switch on the front. Again, they're well insulated, these spade connections onto the on-off power switch, but I wouldn't take it for granted. We've obviously got a chassis rail nearby, so potential for a severe electric shock between the live and earth is possible. We're not sure if his heatsink's alive as well, regarding the low voltage side, so potentially there could be an electric shock hazard there depending on what voltage is present there. So there's quite a few hazards in here. There's a fan spinning as well, so you could get your fingers in that. There's all sorts of safety hazards, so always be careful when working on these kind of power supplies, that you respect the mains and that you don't touch things that you don't know are possibly live. So word of caution. But anyway, getting into it, we've got the usual power supply configuration, and we have the obviously the mains transformer in the middle of the unit, which is the heaviest big laminate transformer. It's not toroidal in these, it's a laminated version. We've got the reservoir smoothing capacitors on the rear, which is for the DC output. We've got the bridge rectifier, which we can see down here, which is bolted to the heatsink. And then on the heatsink we've got a thermal shut-off as well, which, as you can see here, just there, that's a thermal mechanical switch that will no doubt, if a heatsink gets too hot with the load that's been taken from the supply, cut the electrical supply off to the or shut it down at the very least. And then we've got a series of transistors, probably about 4 I think with the look of it. I think these are 2N355 NPN power transistors, which are bolted to the heat sinks in the unit. And we have 2 layers of heat sinks. So obviously the collector of the transistors goes off to what was the output supply from the bridge rectifier. The emitters of the resistors go to these emitter follow resistors, which then balance the outputs equally across all the 4 transistors before converging those together to be the regulated output. And the base of each transistor goes off then to what is the voltage regulator section on the board, which naturally regulates the supply. So I think what we're going to do first of all is we're going to check to see what voltages are on the transistors, to see whether the biasing conditions are correct, and then take it from there, see what supplies we get around the unit. Back soon. Okay, looking at the architecture of a device, obviously we discussed so far that we've got the transformer whose output is directly connected to the bridge rectifier. Interestingly enough, both sides of the transformer secondary windings are connected to the bridge rectifier. You will see on some power supplies, depending on the cheap ones, where they start to use the bridge rectifier as a half-wave rectifier. So what they'll do is they'll have one side of the output, the transformer, connected to 2 connections on the bridge rectifier, and then the other side of the transformer will go straight to the negative terminal on the front of the unit, and that will be the reference then for all the negative side of the supply and regulators and all the circuitry to go from that point, as well as the output. And they'll actually link the bridge rectifier together in such a way that they're using all 4 diodes as a half-wave rectifier, and that way then it can provide a higher output current then than one on its own, with both halves of the cycle rectified as a 100 Hz full wave rectifier. So you will find that in some power supplies there'll just be a big thick piece of wire linking diagonally across from one side to the other, and one big fat chunky red wire coming off, then that'll go to reservoir caps and then to the series pass regulators. And I have seen that on some supplies, but it isn't on this one. Both the black leads coming out the secondary of the transformer connect to the bridge rectifier. So looking at the current format then that we've obviously got the live coming in via a switch into what is the primary side of the mains transformer. Again, on this one we've got a double pole switch, so the live and the neutral paths are supplied with a switch, so for isolation. Then with an earth connection as well, which goes to the chassis of the metalwork. Then on the secondary windings of a transformer, it's obviously a step down laminate core. It isn't a toroidal with a ferrite core, so it's a laminate core transformer. Then we take that, in this case, to the bridge rectifier directly. So we have a full wave bridge rectifier with the 4 diodes orientated in this fashion within the package, and that then provides our positive and negative output. So, and that's the AC waveform there. So obviously the reservoir capacitors are down here, and there with the thick black and red wires tagged straight onto the bridge rectifier. So these are the big reservoir capacitors to smooth the ripple from the bridge rectifier. So obviously at this point here, without the reservoir capacitors, we would literally be having this kind of format at 100 Hertz. So because here in the UK we have 50 Hertz supply, as soon as both halves of the output of a transformer are rectified, it doubles the frequency to 100 Hertz. So basically having the reservoir capacitors in will then smooth out basically the supply, and these gaps effectively get filled in, so we get a nice constant DC output. So with the capacitor then the voltage looks like that. So that's basically what we're looking at. and that being time, and this being volts. So these reservoir capacitors are quite important. A lot of power supplies, particularly the older vintage supplies that I'll show on this channel, have giant capacitors in them in comparison to this. These are quite small capacitors, but some of the capacitors that I have in my storage boxes here are bigger than, well, basically beer cans. And they used to be used a lot in computer power supplies in the days before switch mode power supplies became widely available. And they have high peak inverse current rating, because obviously when we're drawing a load across the output here at high current, the capacitors are going to be discharging in between these peaks. The capacitors are going to be discharging their charge into the load, and although capacitors can have a high microfarad rating, I mean we could be using somewhere like 50,000 microfarads here, the current, the inverse current that's removed from them when the charge cycle from the bridge rectifier leaves and it discharges, the charge in the capacitor which fills these gaps here, depending on the peak inverse current rating of these capacitors, will denote how quickly the charge escapes from those capacitors. So it's often the case that the small little diameter capacitors, like what they use in here, have quite a low peak inverse current rating. So when we take significant load from the supply, then we start to see ripple just forming, which is where we get obviously the discrepancies between the capacitor being able to discharge and maintain that charge sufficiently in order to keep the supply ripple at minimum. And so generally the larger the capacity, the big beer can type capacitors may have like 15 to 20 amps peak inverse current rating. There might still be the same capacitance as one of these, it's a 20,000 microfarad or something, but they can take a hell of a lot more oomph when it comes to current being dissipated from them in between the peaks where we're charging the capacitors from the bridge rectifier, between the cycles of the mains frequency. And so therefore the larger the capacitance doesn't necessarily mean that the supply will be able to tolerate a high current load, because the capacitors themselves might have a low peak inverse current rating but a high capacitance rating. And so that's the trade-off really, and obviously the bigger the capacitor, the bigger the power supply needs to be in order to accommodate it, and thus we can end up getting into design limitations then when it comes to supply design, where I want to make something compact but yet does the job. So what we've got to do really in this supply, we've got two large electrolytic capacitors that are mounted on the PCB down there. I'm not sure what capacitance rating they are. Let's have a look. I think we can zoom in on them. I think they're 35 volts, and the manufacturer I've not heard of. Oh, they are, look, 27,000 microfarad. So there's 2 times 27,000 microfarad capacitors there, which are obviously quite chunky. So these are 2 times 27,000 microfarad capacitors, okay? And then what we have coming out then from here is we've got them then going, the supply from this bridge rectifier going off to all the transistors. Now there's 4 transistors on this particular unit, and so they will be 2N3055s more typically, which is used on this kind of supply, and these are NPN transistors, and these are widely used in power supplies for high current output situations. There is another transistor which is the equivalent of a 2N3055 that's widely used in power supplies, which is a 2N3771, which has a collector emitter current rating of 30 amps, whereas a 2N3055 typically has a specification of just 15 amps, and so therefore it can tolerate less load and thus heat up quicker depending on the load output. So all the collectors of the transistors are all joined together, all the 4 2N3055s, and then basically the emitters go through these cement resistors. Now there are 4 cement resistors, 3 at the top, 1 at the bottom. So then we have these emitter follower resistors. The job of these resistors is to balance the output. So in other words, all the 2N3055s are carrying the same load as one on its own, whereas if we didn't have that, there are slightly different HFE characteristic values, unless they're all matched, where some will be slogging the guts out more than others, and so the load without the emitter resistors would be unbalanced, whereas with the inclusion of the emitter resistors, then we would obviously balance the outputs. The current will be shared more equally across them all. So if you imagine all these joined together, the base connections of that, and then we have on this little PCB down here, which you can barely see, we have a TIP, I think it's a 31 or TIP 41 transistor bolted to the heatsink there, and that's our Darlington driver transistor. So we have another NPN transistor, which in this format being a Darlington gives us more current gain, and it's in one package, and therefore that's what that is. So this is our singular device there bolted to that heatsink, and this also has a connection to the collectors of these transistors for getting its supply, and there will probably be a resistor as well on that PCB down to the what would be the chassis ground. This will probably go to the chassis as well, negative. That will too, or neg VE, and then or 0 volts. Then that then will go off to our PCB. Now the PCB will then consist of all the voltage regulator element, which we'll look at shortly. This would then have some more capacitance on the output, not particularly big capacitance, but just enough to filter out any noise that might be on the output. Also give some kind of suppression as well to any variances of the output swings, so that it's more smooth, and that will then be taken to the plus terminal. There doesn't appear to be an output fuse at all or anything like that to protect it, so, and that would then connect down to chassis, which would be the negative line as well. So this is where we are at the moment with regards to a common design with these. These are normally 2N3055 transistors, and these are normally what fail. Either this transistor can fail and go short, or there can be some other issue where we have one of the 2N3055's biasing conditions alters, so therefore it basically conducts between collector and emitter, and thus it can conduct fully. Or it could be a biasing issue on the PCB where it's providing 25 volts bias here and basically switching these transistors on fully instead of regulating the voltage. So it could also be that. There could be multiple faults here, multiple issues, but we'll have a look at that next and drill down into further detail. Okay, so as far as voltage regulation is concerned, in days gone by in power supplies, we used to have what's called a Zener diode reference. So basically we'd have a resistor. This could be quite, depending on what it was driving, could be quite watty, this resistor, and get quite hot, but basically then we would have the Zener diode then in circuit. And I have a selection of Zener diodes here, but they're all rated different voltages. And obviously in this case we would select a Zener diode if we wanted a fixed output as say 12 volts for example. We might select a 12.6 or a 13 volt Zener diode, because the 0.7 volt drop between the base emitter junctions of the transistor would have to be taken into account in all the different stages. So, you know, we might have, for example, a 0.7 drop there, then another 0.7, so a 1.4 volts drop cumulatively across the system. So therefore we need to account for that with the Zener diode. So that's one particular method of doing it. Now, the formula surrounding what the resistor value would be there, depending what the current is present at this location. Then we would take the load, the V and the I, from the volts and the current from these 2 points here, or we could develop it across these 2 points depending on what we're doing, but quite often most circuits will be in this format. So this would limit the current and that would limit the voltage, and therefore depending on how much current we have going through here, if this is say a 20k resistor for example, and that's a 5.6 volt Zener, then the amount of current that we can take from this circuit depending on the value of that resistor. And so the volts divided by current, the VIR triangle basically, would denote what that would be. And there's, as I say, formulas working this out. So for high current power supplies of yesteryear, where this would be directly driving a transistor, for example, in this sort of fashion, and that was to go to the load, then we would need to calculate the current properly for that resistor, because as we all know, when we load a transistor on the base, bias it with the current, that would also be on the emitter. So as we take the load, it not only loads the current coming from the collector to the emitter, but it also absorbs the current flow from the base. And so therefore it would make more sense to have that current gain into another transistor, and then that itself would provide the current gain to the load instead. So that basically would allow us then to not influence so much what the current is provided by that resistor. And so therefore the current taken by this transistor to provide to this one would only be very low in comparison to if we had the load off the first transistor directly. So there's these kind of circuits that are widely used within power supplies even to this day, Zener diode reference circuits. We've also got the fixed voltage regulator, or what is the 7/8 series voltage regulators, where we basically have an input, a ground, or we have negative voltage regulators as well as positive voltage regulators, and then we will basically feed that to what is our coming off our bridge rectifier, the full potential of the supply, and then the output then will be 12 volts. These can provide up to roughly anywhere between 2 to 5 amps depending on the size. Most of them come in TO220 packages, but they're also available in TO3 packages. There are also variants of this, the LM317 I think it is, and the 31 something T regulators that are in a TO3 package, like these 2N3055s, which are adjustable, so you can have a potential divider or a variable resistor in the leg, and then you can have an adjustable voltage regulator where you can turn a potentiometer, which will then adjust the output voltage. So there's that as well you can have. There are all sorts of different configurations, and then there's IC variants of it as well, which provide low current, which is probably what's used on this supply, which then drive a transistor and thus drive the series pass regulators. So there's all sorts of different things, and obviously in this power supply as well, we would need to measure current by dropping the current across a resistor, and then that would then potentially provide an ammeter. So basically across the emitter resistors, or one of the emitter resistors, then would give you the ammeter reading. So that's also can be read off as well in other ways, but that's just a basic version of it. So it's using the emitter resistor as a current shunt. So there's all kinds of different voltage references, loop backs and op-amp circuits and various other things that can then derive the total output supply regulation. And then of course these circuits don't provide any feedback, of course. So if the current provided here is, say, 30 amps, and then we start to take 30 amps, and voltage starts to drop dramatically because the output of this is loaded severely, then we might want a feedback loop connecting back to an op-amp circuit, which would then regulate the output more closely. So for example, if we drew 20 amps instead of 30, then the output voltage might drop to 10 volts instead of being 13 volts if we wanted that, and thus we would need to have a feedback loop into a reference circuit, and then it would compare the output versus the input to the regulator, and then it would then adjust the output current accordingly to drive the transistors harder, so therefore the output voltage is maintained along with the current. So there's all kinds of different regulator circuits, etc., but we'll look at that in further detail once we get this board out into more stripped down condition. Well, just to show you anyway about Zener diodes, we've got a selection of them here. I've put one out of this bag here. These are 18 volt Zeners, which are these big beefy ones, and then we've got the smaller ones, you see, which are these. This particular bag's rated at 15 volts. So these Zener diodes will be there in that bag rated at 15 volts. As you can see, the size of them is massively different. And obviously when we're using Zener diodes with resistors, then typically we would have a formula for choosing the resistor value. And naturally the scenario that we've got here to consider is the amount of current that's provided, not just the voltage. So if we've got this set at 20 volts DC, for example, that's at 0 volts. The voltage that we will get across these 2 points here will depend on, obviously, with the value of the Zener diode. So for example, in this case, if we were using a 15 volt Zener, and that was 15 volt rated, then we would get equals 15 volts there, but then the current would depend on what we're needing to supply here, and so that would depend on this resistor. So we will call this R, and that's ZD. Now, depending on the current that we need here will also depend on the value of resistor and its wattage. And what you've got to remember with Zener diode circuits is, even if there's no load consumed on the output, this circuit's still consuming power. So it's quite inefficient insofar as efficiency is concerned for power consumption. So if you're using a Zener diode that's this size, where it's rated to give many amps regulation, this then can be driven by a very, very high wattage resistor in order to develop enough current across it for an output, which could drive, say, a heater element in a CRT tube, a valve, or for example it could supply another option, say an industrial machine, a voltage for an electric motor or an actuator or relay or something of that nature. So naturally these are power Zener diodes. In cases where we're using power Zener diodes, this resistor here, whatever value is selected as part of the formulas for working that out, and obviously we can use the VIR triangle in order to work out the voltage current resistance required. But in any case, it doesn't matter so much because it's the wattage of a resistor, and volts times amps equals watts. And so in this scenario we would need to select an appropriate resistor wattage to then absorb the heat that's generated from the current, which is then produced by the Zener diode regulating the supply at 15 volts. Now the voltage drop across this Zener diode, if you like, or across the junction with this resistor, in this case, because the Zener diode's at 15 volts and supplies 20, there's only 5 volts dropped across it. And so therefore, when we consider the value of resistor in comparison to, say, if this was a 3 volt Zener, where we're dropping more voltage across it, then the power factor of this resistor will change depending on the voltage that we have in the Zener. So where you've got high voltage circuits like 90 volts and you're wanting to say get 15 volts out, or on a TV or a CRT circuit, something like that, which you commonly see these configurations, then there's a massive voltage dropped across this resistor, and thus the power increases as well. And that's why sometimes you see where these resistors and diodes are mounted on PCBs, slight scorching and burning because they're running hot all the time. Certainly would in this case with that type of Zener diode. So there's a lot about how to select the right resistor and Zener diode for a particular task. Obviously whatever current we want out here needs to be in mind when selecting this resistor, because we can obviously choose a resistor wattage and value which would then equal the amount of current that's available to be consumed by the load, which will be developed across these 2 points here. So that is also another consideration. So you get quite complicated arrangements with these, but as I say, whether a load's been taken or not, this resistor is always hot. It's always running under load because the Zener diode's clamping it down to the voltage that we're wanting to regulate at. Nevertheless, these circuits are still widely used in power supplies like these to provide a reference. Typically they use glass Zener diodes like these because we only need small currents. And so typically we would have, say, a series pass regulator transistor. In this case it's a 2N3055 NPN. We would take a sample of the output of the 2N3055, what would be the derived across the output terminals. We would then feed that into a comparator basically, and what we would do is we would in this comparator we would feed on the non-inverting input, whichever the reference signal, the Vref, okay, and then this is what will be the V out. And basically inside the comparator you've essentially got 2 op amps, and then the output from that then would be potentially driving this 2N3055. And so what we're doing here, if we say wanting I don't know, let's say for example 15 volts out, we would use the 15 volt Zener as a reference. This supply voltage here might be, say, plus 20 volts DC, and thus the two are compared. Now if we introduce a load which we will call RL, and this then is, you know, that's positive and that's negative, or 0 volt, across the output of the power supply. When we introduce a load, quite often the transistor's regulated output will drop. It will start to drop as an effect of current being drawn from the transistor and the load increasing. And thus, if we didn't monitor that, then there's a potential for the output of the transistor to fall off, particularly at high current loads, and thus the transistor will not be able to regulate the output. And so by and as well as that, the collector voltage will decrease as well. So the whole supply to this device plus what's on the output will start to shift depending on the load that's being taken, particularly when we get to high currents. So by taking a sample of the output and then feeding that into a comparator and then comparing on one of the gates of the comparator the voltage reference from a stable Zener diode reference, will then ensure that the output is compared to the voltage reference, and thus a feedback loop of regulation will be achieved, and thus the output then will be maintained until such time as a load increases to such an extent where the supply voltage to the transistor cannot be maintained, and that might be when we get to about 30 amps in the case of this power supply. So it doesn't matter how complicated a lot of these power supplies are. There could be several ICs on here and all sorts of fancy bits and bobs, but somewhere on there will be a Zener diode or a precision reference. You can get these days ICs that are in different packages that are precision references. Sometimes there can just be two-legged devices or three-legged, depending on what kind of device they are, but generally speaking, they're basically like a Zener diode and a resistor, all integral within one package. You know, you can do that. There are also fixed supplies as well, or even variable supplies, like for so we've got these 7812 voltage regulators here. These are fixed voltage regulators. These are really useful. You make your own power supplies out of these things, but basically there's a box of them here that I've got that's got different values in different voltage outputs, but basically these can be used as reference sources as well instead of as Zener diode configurations. Obviously the unit cost of these is higher than a Zener diode resistor, so when you're making, obviously getting down to the component count on designing power supplies, you may wish to choose a component that's like these two because the costs are less. Get the same result, but costs are less. Obviously, insofar as this is concerned, the voltage that's present on this point of the supply can go as low as 15 volts before it starts to have an effect on whatever output voltage is. Below 15 volts, obviously this will drop with it, but up to 15 volts then. So there's large variances, if you like, in swing that can occur on this line before it would then be affected. In this case, that would be like 15 volts there, and perhaps there's then a diode peak voltage that it can take across. It might be, you know, as high as 70 volts. So it all depends on the rating of that component, but obviously the resistor takes the brunt of the load, and obviously, you know, would sweat it out if a voltage increased beyond what the selection is for this particular part of the circuit. As I said, there's precision references that you can purchase as well that are basically this combined. These 7812s are quite useful because we can use the 7812 in this area where we have a fixed voltage regulator. The 78 series, you can make your own power supplies out of these if a low current. Generally give us, for example, a 7812. The clues in the part number. This, for example, will give 12 volts out. The 79 series gives negative voltages as a negative voltage regulator. 78 is positive voltage regulator, available in 7805s, 06s, 08s, 09s, 12s, 15s, various other voltages as well. So you can select them. They'll maybe give 1 or 2 amp output. The input has to be around about, I think, 3 volts higher than the output minimum. Otherwise then the reference circuits within the regulator can't compare the input to the output and thus keep it in regulation. Generally speaking, there's the center tab of a TO220 device is to ground or 0 volt connection, so that would be 0 volt or neg VE, whatever, and this will then be the output. I have seen hacks where people have put diodes in the ground leg to then increase the reference voltage that's developed internally. So for example, it will give 12.7 volts out instead of 12, so that can be a little bit of a hack, especially if you're using it in this scenario where it's connecting to a transistor. So you can make up for the losses developed across the base and emitter of the transistor. There's all kinds of things as well. There's the LM series regulators, which are exactly like these. Again, they're in that box where you've got an adjustment pin. So for example, in that scenario on the LM series regulators, you've got the, again in a TO220 package, You've got the volts in, which typically on one side, that volts out on the other, and then you have an adjust pin, which again will then adjust a potentiometer, where you can then get the voltage. Again, depending on what the Allen part number is, will denote on what kind of voltage output, but that might, for example, give you 0 to say 20 volts output if the input is, say, at 20 volts DC. These are rated to all sorts of different voltages and things, so you can make your own variable power supply. Again, typical 1 amp to possibly 2 amp current provision. Once you go above that, it'll go into shutdown or limiting, so they're quite useful. You can make your own power supplies with those. In addition to that as well, they do the TO3 style LM series adjustable voltage regulators, which are like the 2N3055s being in a TO3 package. So it's a larger elliptical sort of device. It's more like an egg in shape, which you'll see when we get these 2N3055s off. And then we've got the centre cap in the middle bolted down to the heatsink. That's what these are down there. And these can provide up to roughly 5 amps. I've typically seen them. Again, LM series voltage regulators. So again, you know, we've got 2 legs. The collectors, the input might be the shell, the body, and then you've got the reference and the output. Reference obviously goes to potentiometer, that kind of thing, or it could even go to a voltage reference to provide then a high current fixed output. So in other words, it replaces the necessity to have a series pass regulator transistor on its own. So there's all kinds of different designs and things, and if you're good at improvising with electronic components and selecting different components for different applications, you can actually make quite a nice little power supply yourself, or use these as a voltage reference. It's also an adjustable, and you don't have to go to a high component count and thus increase the cost of your design, just by using minimal components. That the design that's gone into these components is so advanced that not only can they provide a stable output voltage within a very tight tolerances, but also they provide excellent current regulation. And bolted to a heatsink obviously improves the longevity, but also ensures that, you know, you can make a very reliable power supply with both thermal shutdown capability, current regulation capability as well. And indeed there are current regulators that you can get in the LM series range as well, where you can adjust the current as well as the voltage, and they tend to have 5 legs on the device instead of 3. So there are many different components that you can buy, and obviously then improve your designs. So there's all kinds of different circuits and things that we've got in here, but I think these are them here, if I remember rightly. I think these were the programmable current ones as well as voltage, I believe so anyway, I could be wrong, but yeah, I think they were them. So these are where you've got the LM 2575T adjustable voltage regulator. So these are both, I believe, current adjustable as well as voltage adjustable, hence why they've got the additional pins on them. So yeah, again, these are very useful as well. So you can really do a lot with them, you know, there's so much you can do, it's unbelievable. But again, in the context of this power supply, we've got this similar thing going on here. We'll have a voltage reference being provided to then be compared with the output, and thus then create the regulation for the series pass transistors mounted on the heatsink. Okay, so what we've done, we've isolated all the base connections to each of the 2N3055s. This PCB down here, we've removed the desoldered from this land here, all these wires. Interestingly enough, there is a wire that comes from this PCB which solders to the same island that the bases to all these transistors connected to on the output of this transistor here. So I'm wondering if that goes to the voltmeter even, or something of that nature. I would doubt it, but you never know. Might be measuring the base as opposed to the collector, the emitters rather, output. Seems a bit strange to me that, but anyway. So this was soldered to the same land that all the other 5 base from the 2N3055s were soldered to. So I wonder if this is some kind of monitoring loop back thing. I'm not sure because I don't know what's on here yet. But top and bottom of it is, what we've done is we have, get my pen, we've got, as we saw earlier, we've got 5 2N3055s, which are in a series pass arrangement. Drawing this configuration. Run out of space here. That many transistors on this. Must have had £1 million budget on 2N3055s. So we've got 1, 2, 3, 4, 5 transistors. Now basically what I've done, all the collectors are all connected together. All the emitters have got emitter follow resistors on them, and obviously those are the white cement resistors that we're looking at earlier on the board, and likewise they're all connected together, and then we've got an output. But what I've done is each transistor base leg, if you like, I've been isolated individually. So that's what I've done. And what I'm doing in this context is, rather than go through the time consuming rigmarole of desoldering everything in sight just so I can check things, I have individually, because these would normally be connected, all the base connections, I've individually removed them. So that way we can do an isolation test of each individual transistor by checking the transistor junctions with a meter on each individual transistor, see whether I can find one that's got a short or a problem with it. So that's how we can test these without having to unsolder all the other wires on the collectors, emitters, etc. So that's what we can do, but there might come a point where we have to undo the emitter resistors yet to test those junctions further, but we shouldn't have to. So we'll do that now. Okay, ready to do a measurement now of the base emitter junctions. Just select a diode test, press enter. We'll connect the negative probe up to the emitter resistors. Just double check that we've got a reading by touching this emitter resistor, and we have there. Right, okay, so I'll try and do this one-handed. So the very first transistor, which is this one here, we'll measure that. We'll just get this probe on, obviously one hand on the camera, and we're reading 0.562 forward. So that's that wire. The next wire will be this one, which is from this transistor down here. Again, let's have a look at that. 0.562 again, so that's okay in that direction anyway. Just having a look, see where, if I can find the other wires. This wire is, looks like it's from one of the transistors at the back on the lower deck. So this is transistor number 3, and that, if I can get on it, because it's a devil with just trying to work with one hand, damn it. Okay, that's okay. So that's transistor 3, I think. Yep, transistor 3. There should be another wire somewhere. That black wire is for the thermal, and those are the 2 that we just measured at the top there. So they're okay. That's the that's one there. So that's, let's just measure that one. So that's transistor 3, we'll call it. That's okay. that was transistor 4, the one we just measured just a few seconds ago. So that's 4 transistors, that's that one. Something not right there. Oh, my bloody lead's come off, hasn't it? Put that back on, there we go. So this is transistor number 4 then, is this one. And we're okay there. And transistor number 5 is this awkward devil down here, if I can get to it. It's a short lead. It's really short, is that one. It's a real pain to get to, is that. Right, we'll connect up to that one. What we got there? Aha! Looks like it's short then. We've got a short circuit. Base emitter. Well, it'll be interesting now to find out what we've got. Collector emitter. So we'll do that now. So the collectors are on this little stud here. You can just see that tag there sticking out. That's a collector. So we'll just go on there. And I just want to read between the collector and base. So obviously we've attached the negative probe now onto the base, and I'm going to attach the positive onto the collector. We've already identified that by making the base positive and the emitter connected to the negative probe, that there's a straight through connection, a short circuit, which there shouldn't be. There's a dead short across that junction. So I just need to check now to see whether there's a short between collector and base, or a short between collector and emitter. So we've got a short one way anyway, which isn't good. So let's just see what we've got between the base and collector. So we've connected the negative probe to the collectors, which are all joined together anyway, and then we just need to find that little wire again, which is there, and just get on that. So let's have a look here. So yes, it's short circuit between collector and base, which is interesting. So basically what would happen in this scenario, because all the bases are joined together, and then to that transistor board there, all the bases connect together. In this case, if a transistor's gone collector base short as well as base emitter short, it's not so much the issue with base emitter short, although that's not good, don't get me wrong, but collector base short means that because we've got 25 volts here present on the collector, supplied from the reservoir caps and the bridge rectifier, if the short circuit exists between the collector and the base, the 25 volts is going to make it out onto the base. And seeing as they're all connected together, basically, if we draw that in so it's easier to understand, seeing as it's all connected together, excuse my horrible drawing, but basically it means then that we have 25 volts present on here. It'll track down onto the base, come all the way along, and then obviously go up the next transistor, and all this transistor is working fine. It'll bias this full on to conduct fully across from collector to emitter, and thus it will do that to all of them, and thus it will cause them all to conduct on full on at full 25 volts. Whatever's on the collector will be on the emitter, because it will be switched full on, hard on. So having that one transistor short circuit between those junctions means that it affects the other 4 with the bias conditions, and so it would obviously cause a major issue, and that's what we seem to be getting here. Both the collector and base emitter junctions are short. It'd be interesting now to find out if a collector emitter junction is short circuit. So we've got the negative probe on the collector. I can just go straight onto the emitters and see whether that's short circuit, and it is, which is interesting. So let me just go to continuity go to continuity. Yeah, so that's interesting. So now I can isolate that further by now tracking the emitter wire from that transistor when we can find it. I think it goes to that first transistor. I'm sure it does. Let's have a look, see whether we can see inside. So that's the wire there, the one with the fault on it, and it looks like it goes to the rear. There's a transistor up the rear, I believe. So there's one up there right at the back, and just see it hiding away, and that's where that one goes, right up the rear. Yeah, so it's a transistor that's down here, buried at the back. So the emitter wire from that transistor, which I believe is this thing here, I think it is. Yes, that's the emitter wire. And if I track that, remove this, unsolder this emitter wire, that'll isolate that transistor from the circuit. So in other words, we're taking it out, and that way then if we shouldn't get the short circuit then between the collector and the emitter, one would hope. And that way then that proves that that one transistor's gone collector emitter, collector base, base emitter short. So all three, well, all junctions of transistor have fused together. So right, we'll have a look at that anyway just to prove it. Right, we've unsoldered the emitter wire that comes off that transistor that was soldered down here. So now when I test there, the continuity is reading open circuit. So that means the other, we've isolated that now. So basically we've got the base is isolated, if you like. So, and we've also isolated the emitter as well. So we've currently got our meter connected between the collector and the emitter on this transistor. We're reading a short circuit. So if I go on to that emitter wire now and touch it, I see we're getting a short circuit. So that's basically where we've got the meter now. If I were to now touch the because we're on the collectors, which are all currently joined together still, all the collectors that go into each transistor, if I would now to touch that on the emitter resistors, okay, any of them, I'm not getting any continuity. So that is basically me having a wire, the meter across all these together. So basically we've now got our meter connected onto the emitter and then onto these collectors, and then we've got two metering points. So that point there is what we're looking at now when we touch the emitter resistors here, because we've got the neg probe on the collectors that are all joined together, and we've got the positive probe on all the emitters that are joined together on the 4 remaining transistors, and they're all reading open circuit. So that proves that these junctions are operating correctly as they should be. And if we then, now we've isolated that one transistor on its own, which is this wire here, then we get the short circuit. So, and that's dead short. So that means this transistor's gone in 2 ways, which is quite unique, because normally transistors can go between collector emitter junction, but they're also between base emitter. So, you know, but this has gone both ways. So basically it's gone that way as a solid short, and then it's gone that way too as a solid short. So all 3 points from the collector the emitter and the base are all shorted out. So that's a problem, that, because obviously anything on the collector would end up going out back to the other bases to bias all the other transistors on fully. Also it's dangerous another way, because the collector is short to the emitter, which means the full potential of a supply on the collector now finds its way onto the emitter. So it doesn't matter what these transistors do, even though they might work correctly normally, it doesn't matter, because the output then suddenly, as far as volts concerned, would, during a normal, before the fault condition occurs, be a steady output at the correct voltage that it should be, say 13 volts for example, and then suddenly it will go, when the fault occurs, right up to the full potential what's on the collector, which in this case is around about, let's say for example 25 volts. It's probably a lot more than that, but I think we measured 27 volts, 28 volts. Just play around about that on the collectors of these transistors. And so if you've got a piece of equipment on the output, it's going to damage that piece of equipment if it's only designed to run at 13 volts. So that 2N3055 is well and truly screwed. These are all okay. We've checked these. We can do an inspection of obviously the collector base junctions now of each one of these transistors to see whether they're okay. I suspect there will be, but I'll do that anyway. So we can just reverse the probe round the other way and check those, which we'll do next, and that way then that'll prove those junctions are working fine as well. So when only we're checking the base emitter junctions, we'll then check the collector base junctions of each transistor as well, just to make sure, because when we get this apart to replace this defective 2N3055, while it's apart, if there's any other transistors that are knackered, then we may as well change those at the same time. What we don't want to do is rush in, change that one transistor, put it all back together and find out that there's still a problem. Maybe a couple of transistors that aren't balancing the load properly because the collector base junctions have got an issue. So we'll have a look at that next anyway and drill down further. Okay, so here we've got a 2N3055 out the parts bin, an ST model, and we have, if you like, the underside drawing of the transistor, which is as we see it now in this fashion. So basically this pin here is the base connection, the pin on the left is the emitter, and the shell, the body of the transistor, is a collector. Now obviously, as the test that we've just proven, the base emitter junction is where we make the emitter. We connect this probe to the emitter, and then what we do then is we'll put the diode test on this point there, and as we can see we've got 0.551 volt forward there. We shouldn't get a reading the other way, which is when we make the base negative and the emitter positive, and as you can see we're not getting a reading, which is correct. So that tests this junction out of the transistor, which is the base and emitter. So that's that area there that we've just been testing. Made sure that the diode only conducts in one way, or the junction of the bipolar transistor only conducts in one way. And then what we do then is we can make the collector negative, okay, to test the other side of the diode, and then we can go on to the base with the positive, and we should get a forward voltage there. However, when we connect to the base with making it negative and then the collector positive, we shouldn't get anything. So that tests, if you like, the diode which is in this section of the transistor. Now we've only done one test here between the base and emitter on all these other remaining 4 transistors. We know this transistor's stuffed, but we've been just doing those tests of one side of a diode in the junction of the transistor, which is this side. We haven't done the other side as yet. So what we'll do now is we'll make the collector on the which is this connection there. That's the connection for that, the collector. Then we'll go onto the base, because we made the collector negative, base positive, and we're getting a connection that way. Okay, and likewise the other way, when we connect, make the base negative and then go on to the collector, make it positive, then we don't get anything that way on that transistor. This transistor down here, do the same again. We'll go on to the collector again, so that's this bit. We'll then go on to the base, and we're getting a diode junction there, which is correct. Obviously we don't want the connection the other way around, so we'll make the base negative and the collector positive, and thus we don't get a connection diode reading. So that's what we can do on all those transistors. So we're checking both junctions of the transistors, both a collector base, base emitter, collector base, base emitter, to rule out any failures in these transistors. Okay, so I've undone the bolts now on the transistor heatsink. Get it off, and then we've got another thermal cut out here, and then we've got the transistors. I've just taken the bolts out, the insulators, now ready to withdraw the transistor. We've obviously got the mica insulating washer underneath it, which is obviously giving its electrical isolation from the heatsink. So we're just in a case now of just getting it out and seeing whether we can extract it without damaging the mica washer. So there we are. Hopefully we can get the damn thing out. Of course we get silicon heatsink compound everywhere, and that's that. So this transistor here is the offending article, so we'll just test it again to make sure we've got the right transistor out, because you never know, I might have got the wrong one out. We'll replace it, put it all back together and find out we haven't fixed it. So let's just verify that is faulty still before we go any further. Okay, so we connected the negative probe of the emitter onto the collector. We'll just bob this onto continuity at least, so that we get an audible warning of a short circuit. So we'll just test that on the shell of the transistor, and that's what we get. Right, so if I go leaving that on the collector onto the base, and let's see what we get. There we go. So 1.3 ohm short onto the emitter, which proves then it's gone collector emitter short. Same again. And then if we go remove the probe from the collector and then go on to the base, make the base negative. It's different when you're viewing it through a camera. Everything looks a lot further away than it actually is. Right, and likewise got a dead short again. Back it on the collector properly between the base and collector, and then also between the emitter and base. We've got a short circuit, and that will be the same both ways. Obviously if we made the emitter negative now, and I can get on the damn thing. And then we went to the base. There we go. And then the same again with the collector. So that proves that the silicon heatsink compound on my fingers, that all junctions are short circuit. And I had that for a while. Normally it will go collector emitter open circuit, so the transistor doesn't work, with the bias conditions, or base emitter open circuit or something like that, but rarely short circuit. Normally they blow open. So I might take this to bits later and have a look inside, saw the lid off and see what's going on inside. I'm surprised at that. Obviously it's a complete failure, quite unusual. So we've got the replacement one knocking about somewhere. If I've not lost it, there we are. So we've got the replacement one that I've had in the parts bin some years. It's time it came out and got put to some use, and I think it's faded a bit on top. It's been some years. Malaysia 2N3055, so we'll bob that one in. I think these are STs actually as well. Let's have a look. Yeah, that's ST as well, so hopefully it'll last longer. We'll see. Right, just transfer the wires over and the mica washer and then reassemble. Okay, we've got it all back together now. The new transistor with some heat shrink on, and this damn stuff Dalcorn in silicon heatsink compound. So now we're ready to bob it back in. Okay, now that we've got the transistor in, which is a procedure I couldn't film because of how complex it was, trying to get the nuts down there again. There was lots of swearing going on when I did that, and it took a while for me to get the nuts on and get everything back to normal. The red wire down at the bottom there, which connects onto the collector of a transistor as well, which you'll no doubt see if I zoom in a bit for you. But right down there, there's another second red wire, which, not this first one, if I just bend that out of the way, but you can see there's a second red wire which connects to that bolt right at the bottom there, just above my fingernail. Then we had to obviously get the nuts and bolts in and the insulating washers, which are highly important. So the next step now, before we reassemble it all, is to just check that where the transistor's mounted, that the insulator, I can get this out of the way because it's all compact is this bloody thing, but basically this insulating washer, we've just got to check that this collector on this can's electrically isolated from the heatsink, because if it isn't, then it'll cause a short circuit. So we've got to just go on with the meter on continuity, and then let's have a look here. Get the probe, just check, short the probe out, and then see whether it so what we do is connect onto the heatsink, flip this damn thing over again. So when we touch the heatsink, obviously, and then we need to go onto the heatsink again just to make sure, then onto the can of the transistor, and there isn't a short circuit there, so that's okay. Likewise, the emitter from the resistor, again, it's all tangled up. So between the emitter and the heatsink, shouldn't be a short circuit, so that proves that the heat shrink round the terminals on the transistor are okay. And there should be another black wire coming out wherever the hell that is. We've just got to find that now. There's a black wire somewhere. Looks like it's disappeared as the black wire. Where the hell's that gone? I've no idea, but it's got to be here somewhere. Oh, there it is, look, it's just disappeared behind the heatsink somewhere there, look. So just get that damn thing out. And likewise, we'll just connect onto that with a probe just to make sure the base lead to the transistor isn't shorted against the heatsink. So, and again, no connection. So ready to reassemble now and resolder all the wires back to where they were. And then we're ready to rock and roll, power it on, and fingers crossed. Okay, so all the wires are soldered back on there on that PCB there, and they're all nicely soldered back on. Got the two wires there, and the rest of them all there. That's done. I've just noticed something as well, actually, when I looked at this underneath. You can see that this temperature thing there, and obviously there's exposed electrical connections there. Be careful with that, especially if you've got it plugged into the mains and you're trying to work on it like this, even though, you know, you wouldn't really do that, but I wouldn't be surprised if somebody did. I mean, even I'd be tempted to do that sometimes, just to have it out, maybe put a bit of card in between them and that. But we've got to be careful of is when you look at this switch here, the mains input switch, this lead here that comes off the bottom of the main switch goes to that thermal cutout, which then goes off then obviously to the transformer. So if you were to have this out a little bit and then put your finger there, or just grab this while it was plugged in, you're going to get a real nasty electric shock, possibly a fatal shock as well. But you know, you've got exposed mains there on the bottom of that, which, you know, when it's buried deep in here behind that, even if you put your fingers down here, not realizing that this has got a main thermal cutout on it as well to cut out the transformer in case the heat sinks on this get hot. So although it's a good safety device to prevent overheating, etc., it's not a very good safety device when you're trying to work on it live like this. You know, if you've got it plugged in and then you just happen to touch that thinking it's the DC cutout like what's up here, it isn't, and it will give you a nasty shock. So just bear that in mind if you open one of these up while it's plugged in. You know, obviously exercise caution there. Put some tape over it or insulate it properly to prevent you from getting a shock. But yeah, it's worth knowing. Right, we've got it all back together, plugged it into the mains. We're ready now to switch it on and see whether we can get it to the 13.8 volt mark. If it works, when there's a little notch here, it's just there's a notch there, you can turn it, and there's a notch there, so there's a notch in there which between the low and the high setting we should be able to get where it says 13.8 volts, the voltmeter needle just there for operating radio communications equipment. So I'll leave the voltage notch there, we'll hit the switch and see what happens. So there we are, good, excellent, it's gone to 13.8 volts. If I reduce the voltage I can get it to go as low as about 2 or 3 volts roughly. That's 5 volts there, then 10 volts obviously, so that's that. And then when we get to the notch should be 13.8 volts, so that's there, and then I should be able to adjust it beyond that about 16 volts roughly, I think, yeah, about 16-17 volts, and then back to the notch, just 13.8 volt, and then bring it right the way down to about 3 volts. So yeah, just noticed though the ammeter has got a bit of a funny thing on it, because when you see the bezel behind the, oh no, I'm gonna have to take it apart again, can't believe it. That'll push against the needle, so when the ammeter works it'll stop it from working. So I need to take the front off again and remove a PCB now that was on the front to get to that meter, to get the meter out, to then take that to bits to repair that now. But before we do that, I'm just going to measure the voltage from the terminals to make sure that the voltage is there and that's correct, so bear with me. Okay, so we've got the meter on behind down here, which is measuring 13.93 volts at the moment, connected to these two front ports. If I turn this down then to what will be 10 volts, I'll have a look, see what voltage. Read that, just off there, yeah, that's 10 volts, and then over to there, so that's 9.873 volts roughly, so that's okay. If I turn that down to 5 volts, again we've got 5.1 volts, so fairly accurate. I think the maximum voltage it goes up to is 16.3 volts roughly. So I wind it back to the notch to 13.8. So that looks pretty good to me. I'm quite happy with that. Very happy with that indeed. So I think onwards and upwards. Now I've got the front panel off again, as you would have it. One of the wires has come off somewhere, so I know where that goes anyway. But still, it's a pain when you get things apart again and then things start failing. Just about to desolder the meter connections, so that I can, using the paste desoldering gun, I can then get the damn thing off the board, release it with the screws. So that's what I'm doing now. Just in the process of doing that. I've got 2 meters to desolder because the meters themselves are fastened to the in 2 places, fastened to the front, so you can't remove a PCB without removing the meters. And I don't know why it ain't wanting to solder down. The desoldering gun's not getting that solder heated up for some reason. I don't know why. It's set to 400 degrees, so it should be melting. There's not much heat conductivity there, so the problem with these older supplies as well is the solder's very old on them, so naturally get problems with the solder not wanting to come off. So that might have done it. So look, see, I'll have to work on that with a bit more solder braid just to remove the residue off it. So just a case of doing these 2 connections down here now for the other meter. Okay, after unsoldering the connections down there, and managed to get to the PCB, having to unsolder both the meter connections and the spring connectors that are at the bottom here. These 4 lugs all have to be desoldered from the PCB. Anyway, looking on the PCB, that's what we've got, and the chip arrangement as well. Potentiometers to set both current and output voltage. But interestingly enough, we were talking earlier about Zener diodes, and look what we have down there. So that'll be where the voltage reference is provided, just there, that ZD1 just there. And as you can see, there's a bit of discoloration around that board in that area where that's been getting warm. Obviously, as like I said earlier in the video, they do get quite hot, some of them, depending on what current's required from them. But that'll be the voltage reference then for a comparator. It could also be that they're using it as a regulator for one of the ICs. So if it's a 5 volt supply on these chips, that'll be a 5 volt Zener, and thus it'll give 5 volt supply to these. Or alternatively, it's used as a voltage reference for these ICs to use and compare the output, so that it can keep everything in abeyance that we're discussing earlier. So the meters that are on the front are held in by screws, 3 screws, so I've got to remove that to get the ammeter off, and then take the ammeter apart and take it from there. Okay, so we've got the ammeter apart now. Out of it, as you can see, the glue on the back of this has failed. It's probably the same with the voltmeter. I'll check that as well. May as well, while we've got the damn thing apart, because the last thing I want is to get this back together after gluing this in situ and then finding out the voltmeter's got the same problem. It's only sellotape stuff that holds it in place, and on the top there, and this sellotape stuff just sticks it on. So what we'll do, got to be careful we don't get little bits of iron filings or whatever in there, in that magnet in the meter movement, because if that happens, then what'll happen is it'll jam the meter from going full way around. I've had plenty of those over the years. that I've repaired. You look at them under a magnifying glass and it looks like an hedgehog, because all the iron filings and things that are on the bench get attracted to that. So keep that in a place where it's not going to attract any iron filings or stop it from doing that. And then we'll just put some adhesive on the back of here, probably some Evo stick, something not really too fancy, just to stick it back down, and that way then that should sort that out. We can zero adjust the meter as well, because there's an adjustment screw on the meter front there, which you can just about see. It's this little screw right in the middle of the picture, and that then allows us to adjust the meter zero position. So that's what we'll do now, and see whether we can get it going. Okay, we've stuck this back on now. We've used this power bond glue that we've got in the cupboard, so managed to get that back on, and it ain't moving, it's not coming off, so that's a good sign. It's on the zero set, so as the old adage, if it ain't broke, don't fix it, so I'll leave it alone. Just put the case front back on, and then let's have a look at the voltmeter, see if that's suffer the same fate. I've had the voltmeter apart and put back together again, that's okay. Just put a bit more glue on the back. It was coming off, it was getting ready to go, but it ain't coming off now. Nothing wrong with that. So put it all back together again now and try again. Okay, so we soldered everything back on. We bolted all the terminals back down. We've soldered these terminals back in, which are the ones on the lower front middle. We've also redone the solder joints for the meter as well, which is these two for the voltmeter and ammeter, and those two as well. And all the other solder connections are all done. All the screws are in place as well, so it's just a case of putting it back together. That black wire that came off, that came from here, solders back to this board again where all the other black wires go, so that's what we reinstated. So ready to put it back together and test it again. Hopefully there'll be nothing else wrong. Okay, so the moment of truth has arrived. Got the meter on behind again, connected up to the front, ready to switch it on, which I'll do that. Straight up to 13.8 volts, and we're getting that on the meter. 13.91. I'll turn that down to around about 5 volts DC, and get the needle bang on 5. It's doing 5.1 volts, and then at 10 volts DC, it's doing 10 volts. So that's all good. The notch is at 13.8, so everything's okay. The warning light's not on, everything seems to be functioning. So I think it's time to just put the case back on and call it a successful repair after that, I think. So anyway, I hope you've enjoyed the video and seen the entire process from beginning to end, fault finding, diagnosis, etc. Obviously this transistor, which is here, is well and truly faulty. I would like to saw this and have a look inside, but the problem with that is that probably going to damage it a lot trying to get inside the can, but we can try, can have a look, you never know, see what we can do. Might be able to get into the transistor and have a closer look at it and see what's gone wrong. Okay, this is a finished article, all repaired, all sorted out, meters all stuck back as it should be. The back plates have become loose and we're touching the needles when you tap the display panels, so meter panels. So if you do get one of these and you get down to that level where you're having to do 1 meter like the ammeter, then always do the voltmeter, because I guarantee to you that if a voltmeter's not got the back plate moving and the ammeter has got the back plate detached and it's rattling against the needle, when you've replaced the ammeter and put it all back together again, that'll start playing up, I guarantee it. So if you're in the unit to that level and you're doing the ammeter, gluing the back plate on there, make sure you take the voltmeter apart as well, because it will be aged enough to do it, and the slightest tap or knock will then cause the back plate to move on the voltmeter. So do them both at the same time. Yeah, so everything's working again. There's no warning light. We've got power light. The voltage was okay. I've tested the ammeter off camera earlier. Put a load on a radio and got the ammeter moving, and that was okay. The voltage adjusts nicely, nice and precise, so I'm happy with it. Just that was a culprit, that ST23055 transistor that had gone collector emitter short, base collector and base emitter short. So it's completely toast, is that. Anyway, we replaced it and got it working again. So with that, I think this power supply is ready now for either selling if I wish to, or I might keep it a while and use it on a transceiver. I've got various ones of these, quite a lot of power supplies in the workshop actually piled up in the corner here. So, and we've got more to look at yet. So but yeah, it's a nice little power supply, does about 20 or 30 amps or whatever. Goes up to a maximum of 30 amps, but it's great for powering HF transceivers and high powered radio communications equipment that needs considerable amounts of current, and quite widely available on the market. Very nice little power supply. They're very compact though, that's the only thing, and they're fiddly to repair. They're very cumbersome inside, as you've seen. The wires come off and spring off the circuit board, so if you do take one apart, just take a few photographs of where the colours of the wires and where the solder on the circuit board. It's not so bad if the wires come off the end where the transistors are, because they're quite easy to find on the heatsink area, but it's if the wires come off a PCB, they're not marked on the PCB where they need to be. So if you do go boing off the PCB when you're pulling the front off and what have you, then take a photo first before you strip it down completely of all the wire connections, colours of wires and where they go, and then you can resolder them back. Otherwise, unless you've got another unit, you're not going to know where they go. Be careful with the safety side of things. Don't have it powered up on mains and touching down here at this side where the main switch is, and that thermal cut-off switch underneath, because there's mains potential on it. Be quite careful with the electrolytic capacitors as well. They do hold considerable amounts of charge, around about 30 volts DC. Doesn't sound much, but the problem is when you got the front panel off and you take the 0 volt connection from the bridge rectifier off this post here, which is held on with a nut. If you've not discharged the capacitor that's floating around inside, obviously because you've removed that from the front panel, if that comes into contact with one of the bolts from the collectors on the 2N3055 or the casings of these, you're going to get an almighty bang as it discharges the capacitor and some sparks. Obviously, if that were to touch as well other parts of the printed board on the front panel here where the capacitors are still charged, then it could cause a nasty short of a capacitor across the PCB and blow the components. So you've got to be careful that you discharge the electrolytic capacitors first before you start working on it, and that way then it minimises any damage to components should that earth lead come off and start touching things, as you would need to do to remove the front panel. Obviously make sure that when you put it back together you just check everything over again before you put the lid on. Just spend a bit of time, have a break, come back to it a few minutes later, whatever, and have a look at the wires and where they are inside. Just make sure there's nothing trapped, pinched, nothing that's come off, because when you power it up there's quite a lot of current there. These little wires can't take much current that you've seen travelling about inside, so one of those shorts to the high current supply potential that's supplied to the collector on these transistors, then it'll just burst into flames. So you've got to be really careful when you're working on them. Anyway, with that, I hope you've enjoyed the video. It's been nice to be able to fault find a component level yet again and replace a defective transistor. and then get the supply working. And if you like the video, please subscribe. There'll be more videos like this. By all means, leave comments below in the video, and we'll look forward to seeing you in the next video. So thanks again. Catch you later. Bye bye.